So one day you decide to launch your very own social media platform. Of course, you'd want to keep track of some useful analytics, like the number of unique visitors. How would you do this? Maybe your solution would be to store a list of distinct IP addresses. For any new unique visitor, store their IP address, and at any given moment, just count how many there are. This works great at first, but let's say your social media platform becomes viral and overnight you have millions of unique visitors. All of a sudden, your list of unique visitor data becomes too large to manage. So how can we solve this problem? We need to be able to get an accurate count of unique visitors while also staying memory efficient. It turns out there's an elegant solution for this. A clever new algorithm that can give us an incredibly accurate approximation just by using a simple flip of a coin, all while using only a fraction of the memory. Alright, so to explain how this algorithm works, let's imagine we have some stream of data. These blocks can represent the unique IP addresses of the people visiting our social media website. Over here, we've got a limited memory pool we can use to try to count the number of unique visitors. The naive solution, as mentioned earlier, might be something like this. For each item, we ask ourselves, do we already have this item in our memory pool? The answer here is no, so we add A to our memory. We go on to B and do the same thing. Same thing with C. And once we come to an item that's already in our memory pool, we simply skip it. And we continue using this method throughout the entire data stream. Okay, so at the end, we see here that we've got 4 distinct items in our memory pool. So of course this works just fine, because we happen to have enough room in our memory pool to store all of the distinct items from the data stream, until we throw in more distinct items. You'll see that now there's just not enough room to store each distinct item. In order to solve this problem, we just need to think a little outside the box about how we approach it. For a problem like this, I probably don't care to have an exact count of unique visitors. I'm fine with just a ballpark answer, especially if I can trade off a little bit of accuracy for some serious memory efficiency. In 2022, Chakraborty, Vinachandran, and Meal introduced an algorithm that does just that. It prioritizes memory efficiency by using probability to compute an approximation. The algorithm caught the attention of the famous computer scientist Donald Knuth, calling it not only interesting, but extremely simple. He coined it the name CVM algorithm after its 3 founders. Here's the basic concept of the algorithm. First, let's introduce a probability factor such as 1/2, like flipping a coin. Now, as we go through each item, we flip a coin. If it's true, the item gets added to our memory pool, and if it's false, we just skip it. So for A, we flip a coin and get true, so we add it to our memory pool. And then going on to B, again, we flip a coin, and it's false this time, so we skip it and go on to C. We continue doing this for each item until we have gone through the entire data stream. At the end, you'll see our memory pool contains 4 items, and each of these items had a 1/2 chance of being added to the memory pool. So all we do is take the number of items in our memory pool and divide it by their probability of being there. This gives us an approximation of 8, which makes sense because if you only take half the items from a group of 8 items, you'd end up with 4. It's important to note that this is only an approximation, not an exact count. Due to the algorithm's probabilistic nature of just flipping a coin, the results can obviously vary. In this small example here, we could have easily ended up with something like 3 elements in our memory pool instead of 4, leading to an approximation of 6, a significant deviation from our actual 8 distinct elements. This is due to our limited memory pool and small data set. The algorithm provides a more reasonable approximation when using a larger memory pool and dealing with more distinct elements because the law of large numbers comes into play. But just for simplicity, I forced this ideal scenario for the video just so I could illustrate the core concept. Okay, so up to this point, our entire stream of data has been all distinct items. Well, what happens if one of the users with the same IP address joins the social media website again? How do we handle that? So continuing where we left off, if we look at these new items in our data stream, the first thing we notice is that G is already in our memory pool. At this point, we can't just flip a coin here to see if we add G to our memory pool again, because that would mean G would have a 3/4 chance of being added to the memory pool, because the first G had a 1/2 chance of being added, and then this G would have another 1/2 chance of being added. What we do instead is just automatically delete the G in our memory pool if it exists there. Then for this new G, we flip a coin. This ensures each distinct item has the same probability of being added to the memory pool regardless of the amount of times it appears in the data stream. So the new G does not get added because we got false. So then we go on to H. H is not in our memory pool, so we don't need to delete anything. We flip a coin and get true, so it gets added to the memory pool. So again, we still have 4 items in our memory pool. We divide that by their probability of being there, and we still get an approximation of 8 distinct items. Okay, now I want to explain the really clever part about this algorithm in the way that it handles oversampling. Let's increase our data stream to 16 distinct elements. Now, in the previous examples, I started out with a probability of 1/2. That was just to help illustrate the core concept of this algorithm, how to estimate using probability. We should actually start with a probability of 1 for a 100% chance that each item gets added to the memory pool. The reason for this is that it could be the case that we do actually have enough memory in our memory pool to store all distinct items. So first, for each item we see, we immediately add it to our memory pool. And as you probably could predict, our memory pool becomes full very quickly and we can no longer add any more distinct items. So at this point, the algorithm realizes it has oversampled. It was too generous with the probability it gave for each item to be added to the memory pool, and it should have started with a smaller probability. So how do we correct this? Well, all we have to do is go through each item in our memory pool, flip a coin, and if it's true, it's allowed to stay in the memory pool, and if it's false, it gets deleted. After we do this, all of the remaining items in the memory pool effectively now have a 1/2 probability of being in the memory pool. And now all we have to do is adjust our probability for future items down to 1/2. And just like that, it's as if we started with a 1/2 probability to begin with. Now we can continue on with our stream of data. But now for each item we come to in the stream, we give it a 50% chance of being added, so we flip a coin. You'll notice very quickly our memory pool starts to become full again. Once it becomes full, the algorithm needs to adjust its probability. So again, we go through each item in our memory pool and flip a coin to determine if it stays. Remember, each item currently in the memory pool already has a 50% chance of existing there. So flipping another coin gives them each a 25% chance of existing there. And after we've done that, we can adjust the probability to 25% for any future items. Now we continue where we left off in our data stream. This time though, since it's a 25% probability, we now need to flip 2 coins and they both need to be true for the item to be added to the memory pool. Once we are finished going through our data stream, we can now calculate our approximation. So we have 4 items in our memory pool, we divide it by their probability of being there, and we get an approximation of 16. Now, of course, because this algorithm only provides an approximation, the answer should be provided with some sort of error bounding. In the paper, they used a form of Chernoff bounds to achieve this. I won't be explaining this part of the algorithm in the video, but I encourage you to take a look at their implementation in the paper. Now, I should also mention that the version of the algorithm I've explained in the video is a slightly different version than what is described in the paper. The algorithm I've illustrated asks for the maximum size of the memory pool as the input, and it has to work with that constraint to provide an approximation. The algorithm in the paper asks for error bounds you're willing to accept for the approximation as an input, and it optimally calculates the memory pool size needed to accomplish an approximation with that error bound. I've got the Python code for both versions on my Patreon if you want to experiment with them to get a solid understanding of the algorithm. Now, getting a hands-on experience is an incredibly effective way to develop a thorough understanding of a topic, which brings me to today's sponsor, Brilliant.org. Now, I'm very selective with my sponsorships, and I only accept those I believe my audience would genuinely benefit from, which is why they're today's sponsor. Brilliant is incredibly effective at illustrating core concepts in math, data science, programming, and artificial intelligence. What sets Brilliant apart is their meticulously crafted curriculum. Instead of passive learning, they offer a fun, gamified experience that challenges you to apply concepts immediately, reinforcing your understanding. Complex ideas are broken down using intuitive graphics and animations, making abstract concepts tangible. As you advance, you gain XP to compete with others, keeping you motivated to continue learning. They've got several courses on computer algorithms like binary search and insertion sort. They've even got courses on neural networks and quantum computing. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/B001 or click the link in the description. You'll also receive 20% off an annual premium subscription. I want to thank Brilliant for sponsoring today's video and thank you for watching.